Hello again, it's Phil Story from Australia. In this video we're looking at a real-life case study. It was a real engagement I was involved in. It interestingly shows how a default setting in a Microsoft config file had an enormous impact on application performance, surprisingly so. And it was the waterfall chart in NetData that really highlighted it. We're going to use all of the NetData charts really this time, and we're going to use our usual NetData controls and introducing a new one, Alt right click. When I was originally engaged, the brief was to find out why transactions at these user terminals were taking multiple seconds and where were those seconds going. So I was provided with a packet capture taken at the switch that one of these terminals was connected to, and from there in those captures I could see that there was local server activity, but there was also HTTP post activity to a server that was somewhere in a corporate data center. Analysis of the local activity, we were able to knock off nearly a second in terms of total time taken for a transaction or for a user function. But the big ticket item was really these long running posts, and from here they looked like they were all server time, and they were relatively small requests and small responses most of the time. So we had to take the investigation to the data center server. So after a week or two I was given some server captures which were taken on a Windows server, and that was the server that was handling all of the post requests that were coming from all of these user terminals. And from a packet capture taken at the switch this server was connected to, we could see the front end transactions and the back end transactions. Although there were several different back-end transactions, the big ticket items were these encrypted transactions going all the way to the USA over a network that had a 210 millisecond round trip time. So the capture was taken there, and from the capture we could see there was a 210 millisecond round trip time. The MSS observed was 1380, so that led me to think that there's possibly an ASA firewall either at this end or the other end. They also observed retransmission timeouts of 1 second, and that led me to think that possibly there's an F5 load balancer probably in the USA. So let's look at an actual packet capture of the front and back end traffic. So I'll jump ahead to the dialog chart, and here we can see in this particular capture there are 4 terminals in 2 different cities, and they come into this front end server that I've named Oz front end, and in turn that server acts as a client going to a back end server which is in the USA. And here we can see that this is where packet losses and retransmissions come into play based on the different colors. So the next thing we'd want to see would be the performance chart. Click this button. So on the performance chart we can see the red transactions are the front end ones and blue are the back end. So here's a front end transaction that appears to have 6.3 seconds worth of server time with a relatively small request and response. Here's a follow up one with a small request but a larger response, 13 or 14k, but still 4 seconds of server time. And then the blue transactions, we see a whole series of blue transactions associated with those 2 front end transactions. So what we really want to see is a packet timing chart. Now normally I would right click on this transaction and plot, and so we can see the packets of it, but this time I'm going to just press the timing button and get all of the client and server connections on the one chart. The reason I've done this time is what we want to observe is that there's one back-end connection, like all the back-end transactions occur on the same one connection, whereas the front-end transactions all come in on different TCP connections, because in this chart, see the different colors over here, each row is a different TCP connection, and these are client and server packets. So we zoom in to the first pair of back-end transactions. So here was that first front-end transaction. Well, NetData Pro has an ability to modify the text in a PCAP. So I've modified the text here. These are not the real names of these services. I'll zoom in closer. Now there are a couple of extraneous TCP connections on the page. To get rid of those we can right click and hide this connection, and because there's just 3 of them I'll do the same thing, and what we end up with is client and server packets at the front end. So in this case this is the Oz front end being a server on this row, and these are its server packets, and this row is Oz front end being a client to a back-end server which is in the USA, and it's a SSL connection. So these are all encrypted, but we can still see the transactions and we can still see how long they took. What's of note here is that this single front-end transaction was a small request and a small response, but it involved multiple back-end transactions, including in this case the TCP handshake where we can see the round trip time, and an SSL handshake, so 2 more round trips spent on setting up the SSL connection. And the poor old person sitting there waiting for this post to occur had to wait 3/4 of a second on 3 round trips to the USA. USA. Now, we go to the waterfall version of this, and we get a much clearer picture. There's the front-end transaction, and here are all the back-end transactions, essentially each on a row of their own. And remember, I've said before, NetData calculates a critical path, and in this case, the critical path is only 2 front-end transactions. But what I can do is, and that means that on the critical path, the whole time is yellow server time. But if I right-click and say, classify this transaction and exclude it from the summary, then that's not in the critical path anymore, and the critical path has now moved to all of these sequential back-end transactions. And we see that our table over here in the top right adjusts to give us that information, and I can do the same thing here. And now the back-end transactions that are occurring in this summary, and we see that there were 30 round trips in total. And that's because at least 1 round trip for each transaction and some multiple round trip involved in delivering this data. So when we look at the back-end transactions, we can see that its round trip time is the vast majority of the total time. And that's also shown as these orange components. The orange is the one-way trip time. So that's all round trip time. That's mostly round trip time, but a little bit of server time, all round trip time. Now what's of interest and what jumps out here is that every second transaction is this 325 request and 85 byte response. 325 byte request, 85 byte response. So there. And they're all, so small request, small response. And if I use the format control window and say categories of transactions, then we get it redrawn, and we can see these transactions. There's 10 of them in total, and they're all on a row by themselves. So 10 transactions at 210 milliseconds. There's 2.1 seconds worth of these things on the chart. Now if I go back to the timing version, we've got a connection opening and a SSL handshake, and we have these various transactions. They're SSL, so we can't tell what they are. But here we can see that this transaction, there's a purple retransmission, and that retransmission is alt drag. So that's a retransmission timeout, and it's a full second. And again, that's a second that the person standing in front of this terminal waiting for this to happen had to wait. So now right-click, plot flowchart of this transaction. So here's the flowchart with client and server packets. The thing we're interested in is here. So there was a large response, 11 packets worth of response. We sent ACK, but the server in the USA didn't see any of these ACK, and there was 5 of them. And the server did a retransmission timeout at this time. So this is a DSAC. So this is the server in Australia telling the server in the US that retransmission was unnecessary. But we have to deduce that these ACKs that we sent didn't make it to the USA. Now what else is interesting about this? Now you see there was more data to be sent. There was 7 packets worth of data still remaining to be sent after these 11. But they were sent as a burst of 2, 4 and then 3. And on the bytes in flight chart down here we see that. So what does that mean? So because of this retransmission, the sender has gone into congestion avoidance mode and has reduced the packets it can send per round trip. So we could have got all these packets in one go, but it took 2 round trips. So that retransmission didn't just cost us a second that it took for the timeout. It cost us another 420 milliseconds of extra round trip time. Back to the packet timing chart, and there again we can see our green diamond, which is the DSAC. What I'll do now is I'll just right click, I'll keep going to the right until I find the next pair of transactions, and we'll zoom into those. Now again, there's 3 TCP connections on the page that we don't really want, and another way to get rid of them is alt right click, alt right click, alt right click, and then if we redraw, they'll go away. That's an easy way to get rid of lots of TCP connections on the page that we don't want. So again, we've got a long front end post, which essentially to service this post at the front end, we have to do multiple transactions at the back end. And in this case, the purple is telling us there was retransmissions here from the client this time. And how far apart are they? They're 300 milliseconds and 600 milliseconds. So that's actually 2 retransmission timeouts from the client. So either they didn't get to the US or the ACKs from the US didn't get back to us. Whatever the reason, that has cost us nearly a second for this customer's waiting for this to happen. There's a transaction that returned some data. So it was only a 3,000 byte response, but it took 2 round trips to deliver. Now while we're here, we'll look in the second post. Here's a very large transaction. So a single packet request, 2 packet request, still 390 milliseconds of server time, but 1.2 seconds to deliver 88K of data, and that took 6 round trips. So let's look at the flowchart to see what this and that look like. So the retransmission timeouts are down here in these client packets. So that's cost us nearly a second, and that slightly large server response of 7 packets was delivered in 2 round trips. And I think that's because we're still in congestion avoidance mode. So that could have been 1 round trip, but it was 2. So that's cost us another 210 milliseconds. And when we come over here, there's a very large request, but no notice, and I'll zoom in, our 88K is delivered in 8 packets, then 9, then 9, then 10, then 11, then 12. And here, in the bytes in flight or the congestion window, we can see 8, 9, 10, 11. It looks like we're still in congestion avoidance mode, and that 88K possibly have delivered in one go, but it's cost us 6 round trips. So if we say that 5 round trips too many at 210 seconds per round trip is over a second again. Now let's come back to the packet timing chart. Waterfall, here again, there's our front end post, and the back end post is 325 byte request and 85 byte response, and every second one is one of those. Every one of these multi-second front end posts involves a lot of back end transactions. We'll just look at the last set. There's some retransmission, and there's another retransmission timeout from the client, 300 milliseconds, and then a further timeout to send the second one. So we've actually got 600 milliseconds of retransmission timeout again, presumably because the small packets were lost on the way there, or the ACKs were lost on the way back. But again, there was a real customer waiting for this post finish, and that's another 600 milliseconds that they've had to wait. What does that look like on the waterfall chart? So to service this one front end request, there's a get, then what I believe to be a post, with some data this time. There's one of these 325 byte request, 85 byte response transactions, and then a real post that was delayed because of retransmission timeout, as NetData points out to us. There's another one of those, and the real transaction, another one of those, and the real transaction, etc. So this front end transaction was nearly 6 seconds, and it had 1, 2, 3, 4, 5, 6, 7, 8 of these transactions, which look unusual, plus it had 600 milliseconds due to a retransmission time. So if we could get rid of these 8 transactions, 210 milliseconds each, that'd be 1.6 seconds or more. And if there were no packet loss, we would have saved 600 milliseconds. So this whole 6-second transaction could be reduced to 4. Just to finish off, let's look at the whole period. And this time I will say right click, plot only this connection. So now we only see the back end traffic. The waterfall chart looks like that. If I do it, plot categories, replot. And the other thing I can do is exclude client time. Now from here we can see there were 74 in total of these 325 byte request and 85 byte response. And overall, if we exclude client time, then round trip time was 65% of the total processing. So what are these 325 byte request and 85 byte response transactions, and can we get rid of them? So it turns out that these transactions are unnecessary. They happen because of a setting of a variable in the Microsoft XML.NET config file on the server. By changing that variable to false, they go away, and all of these transaction pairs become a single transaction, and we remove 8 times 210 milliseconds of round trip time, turning our 7-second transaction into 5.3. And even that was too long because of the retransmission timeout. So what were the observations and some questions that came out? Well, every second that we can eliminate from these front end transactions, because there's real customers waiting for these transactions to happen, every second that we can get rid of is a multiplier effect, because there could be 30 or 40 or 50 people in a queue waiting to be served. And if you knock a second off every person, that turns into minutes of human time when you multiply that out. So the observation was there are many of these unnecessary small transactions, and they have a big impact on front end time because of the large round trips. But even though we get rid of those, one front end post still has several back end posts. So there could be an opportunity to reduce that by changing the code. Developers don't seem to worry about round trip time when they're writing code, and perhaps if they knew about the effect of round trip time, they might put more effort into calling fewer APIs. Another observation here is that because most of these back end transactions have small requests and small responses, then packet losses don't result in fast retransmissions. They result in a retransmission timeout, and on the client side they cost us 300 and 600 milliseconds. But at the front end, a retransmission timeout cost us full second. And another interesting observation to me was that because we had one retransmission timeout at the server, and the server went into congestion avoidance mode, one retransmission timeout at the beginning, and that cost us a second, but it also cost us multiple round trips for every subsequent set of transactions. What it means is that packet losses in this environment are a much bigger deal than they are in what we might call a normal environment. So that leads to some recommendations that we could make to the US service provider. We know that one of their customers has been experiencing this problem of unnecessary transactions associated with posts. So how many other customers might be affected by the same thing? And the retransmission timeout value of full second, depending on how often those retransmission timeouts occur, that could be a big deal. That packet loss in this environment is a much bigger deal than we normally expect it to be. And a recommendation to the app server owner would be to make the Windows.NET server change and get rid of those unnecessary round trips, which we did. And again, packet loss is a much bigger deal. This is what my engagement looked like in this particular case. It was only 5 days of my time, but spread over about a month. There was the initial analysis of the terminal side capture, and that resulted in a detailed 44-page report, which was probably too much. It involved conference calls with 3 different vendors that had software on those terminals, and thanks to the analysis and the data in that report, each of those vendors went back and looked at what their code was doing, and we did manage to save nearly a second of transaction time at the terminal. But the big ticket item was at the server side, and finding those unnecessary round trips, working out what they were. Now, I'm not going to tell you exactly what the fix was, but I will in a few weeks' time. But I thought I'd give you a chance to have a look for yourself, see if you can find it. The packet capture we looked at today was actually a before capture taken at the test environment, so that's why there aren't so many transactions in it. In the production PCAPs that I saw, there were hundreds, if not thousands, of front-end and back-end transactions. But we made the change, we got a PCAP after, and we did show that the fix worked. And the result of that was a multi-second reduction in every real customer transaction and for all terminal types, not just the original one I looked at. Now, given that there's one of the global service provider providing services to dozens, if not hundreds, of corporate customers like the one I was involved in, so far we only know of the existence of one of their customers that has a Windows server. But if there are more of them all over the world, then it could mean that there are thousands of terminals all over the world and millions of real customers in multiple countries. If they're being impacted by multiple seconds, then it could well be millions of human being seconds being wasted just because of a default variable setting made by Microsoft, and probably 15 years ago. I would love to see a packet capture taken here in the USA and help work out if we really could save millions of human seconds all over the world. What about you though? Do you have Windows servers that use SOAP and POST? Do you know what the round trip time is between your client servers and backend server? And if you have a large round trip time, could you be wasting millions of seconds of your user or customer time and without even knowing it? Well, that was a longer video than usual. I hope it was worthwhile, and comment if you have worked out what the setting is. And as I said, maybe in about a month's time I'll publish the exact setting, but I wanted you to have a go at finding it yourself. Bye for now.